Hello, my friend. How you doing? I hope your day went well because my day was super cool right now. From now, I was just back home from a badminton court, and you know, I still, I still can't help thinking about our next video. And that's the reason why I come back. Yeah, and I apologize for playing a little bit more time than I expect, but we gotta be balanced. We gotta balance between life, personal life, playing shits, and our passion. I think that's a good thing, right? Sometimes the world you feel you will eventually only one feelings, my friend. Overwhelmed. We will eventually feel overwhelmed. But my friend, falling down is no longer a problem. Getting up is the thing we should have control. We should have concern, my friend. So, let's get back into the lecture 3, okay? Let's get back to the lecture 3, image reconstruction. So the point is, our last section was about part 1. Our ending section was, let me see, equipment component used for image reconstruction. And today we're gonna talk about data types. First of all, second of all, overview of image reconstruction, and third of all, lastly, summary, baby. So let's talk about it. First of all, Session 1 and the part 2 of lecture 3, data types. Let's talk about data types. There are two types of data, raw data and image data. As you can see, right now we're talking about raw data. So what is raw data? Let's have a glimpse on a definition of raw data. Raw data, sometimes people call it scan data, includes all measurements obtained from a detector array. Let me highlight this line for you. Yeah, all measurements obtained from the detector array. So when we want to talk about raw data, we gotta compare it to image data, because it's just like a twin, my friend, the twins. Yeah, so that's the reason why we gotta compare it. So one of the most important thing, one of the most highlight we need to remember is the raw data requires more computer storage space than the image data. Why? In short, let me explain to you. In short, the raw data is all about all measurements we got from the X-ray beam, or more narrowly, we got from the remaining X-ray beam after going through our body. But the point is, the image data is the data you will get after the data manipulation process. You got a final image, the ultimate image. So that's the reason why I think it's a reasonable thing. So the raw data reasonably requires more computer storage space than the image data. That's it. What we want to know. So I have put some illustration in this slide for you to understand more deeply about raw data. First of all, we got an image reconstruction process. First of all, you gotta see the acquisition, the X-ray beam going through your body part, your organs, and we got a remaining X-ray beam, and it will meet detector, right? And after then, the raw data will be acquired. It means all measurements from all views, all angles. We got a raw data. And after all, eventually, we have reconstructed image data, or in short, you could call it image data. Here, raw data. The data waiting to be made into an image. You can see it? We call it, this is a signogram. So, under the name of the physicians or the radiologists, we don't need to know exactly the mathematical background of the creation of the signogram. Just know that raw data is the signogram is sometimes, usually, we call it the data show up on the signogram. And yeah, just that is a thing you gotta know, you need to know, you need to memorize it, you need to capture about raw data. The data is waiting, which is waiting to be made into an image. It means which is waiting to be manipulated to be the final image data. That's it. So you can see right here, this is the image reconstruction process. So we got a two subset of it, two kinds of image reconstruction process. First of all, let me show you the term first, okay? First of all, perspective reconstruction. And the second thing is retrospective reconstruction. Yeah. So what is the difference between two guys? So just a simple. First of all, retrospective reconstruction process is the process your data or your image produced automatically, simultaneously, concurrently during the scanning. Yeah, you scan it, you got it immediately the image on the screen. And the retrospective reconstruction is the kind of image you will generate it later on. It means the raw data will be saved in your computer, in your data storage, and you will use it to generate another image. Not the image, which is not the image you get when you're scanning. So that's the reason why we call it retrospective reconstruction. That's a simple difference between two terms, okay? Perspective, the image you got when scanning. And retrospective reconstruction, the image you got, the process you evoke after rain. That's it. That's all. And yeah, I got you something I think is an interesting thing because I put in here. So let me bring it to front, okay? So sometimes also in CT and also in MRI, how would I say it? The technique called perspective gating and retrospective gating. So I'm gonna note in here because usually you will hear about those terms, perspective and retrospective, more commonly. Yeah, that's right. More commonly about those terms in a gating technique. Gating, yeah. So what is gating? I want to introduce you. I really want to introduce you a little introduction about gating, and because there are correlation, even though we got the same term, but the point in application of each area, we got I think there are similarities between area, but the point is a huge difference between those areas. So what about just talk about gating first, okay? Gating is a process you will, how to say that, you will get a picture picture in a particular time point or in a particular event. That's it. And one of the most common application of gating technique is the capturing of our hot image. Yeah, hot image. So as you can see right here, this is our heartbeat, right? Wave complex, RPS complex. So first of all, we need to know about what a perspective gating. Perspective gating is you're capturing the picture simultaneously. Means your heartbeat will trigger our sensor, and that's exactly the time we capture the image. So right here, perspective and retrospective is a kind of you will capture. How can I say it? You will, yeah, we take the image. You need to wait until this time to get an image. Don't need to wait. You capture the image all the time series, all the time right here. And after then, you will use this old data to have your complete image. So the main part is, my friend, perspective got an image exact at this exact time. Your heartbeat will be monitored, and at this time, this point, it will trigger the machine to capture your heart and generate image. Your I can say it's generate a part of the image. We got a data from this point, and retrospective is in another way. We still monitoring our heartbeat right here. But the point is we don't need to wait. We don't need to trigger because how can I say there are delay between signal and the capturing activities, right? So we gotta capture all the heartbeat right here. Heartbeat right here. So after that, we will synchronize. We will analyze this. First of all, we got a data of the heartbeat, heartbeat complex, and we got a data of all images right here. So we try to manipulate it. We try to modify it. We try to cut out something useful. So we combine it all. So we got a complete image. So my friend, this is an illustration I've taken from the MRI technique because there's a trade-off, right? There's a trade-off. When you use it, and the CT will increase. I think it's highly increased dose of the patient. But the point is, if you use it in the MRI application, there's no dose. There is no radiation dose in the MRI, so you increase the image quality. Image quality because of this technique. You don't need to. There's no delay, right? So it depends on you. I just want to have a little introduction about those techniques to you to show you that the prospective image process, reconstruction process, and the retrospective image reconstruction process. Sometimes you will hear about two terms, but in another word, in another area. And one of the most common area of this application is gating. Yeah, gating is. We will go to the gating. We will discuss about the gating techniques in some day. I promise to you. And the gating of the city now, right? There's a similarities, but at the same time we got a huge difference between two kind of machine because CT we are working with the radiation dose, one of the most dangerous thing in the world. So but that's the story of another day. We should end it right now. So that's the raw data. We got types of data, raw data, image data. Let me say for a while. So raw data, we just go through the raw data. We got two kinds of image reconstruction process applying raw data, perspective and retrospective reconstruction. So and we got one of the most common traits of the raw data. It requires more computer storage space to storage the data. Okay, so that's all about raw data. Second of all, let's go to the image data. But firstly, just give me 5 seconds to drink my cup of water. Okay, just came back from the badminton court, my friend. I'm drained right now, thirsty. Oh, I was dying to drink some fluid. So, my friend, image data. We will go about the same process like the former slides. Raw data. Let's talk about image data. And first of all, let's talk about its definition. First of all, the raw data is a result. Our computer has processed the raw data. As I said above before, raw data image data means the ultimate data, the ultimate image. Okay? Means so what is exactly computer process raw data? Just later. Yeah, it means you will assign to each pixel to one house view unit, one particular my friend, one particular house view unit. So what does it mean? Okay, so let me introduce you. So our picture right now, our picture is about 2D, right? Two dimension. And 2 dimension means we got a matrix. You have one about 1024, 1024, 1024, 1024, or 101, 562. Yeah, depends on matrix. Here it's a matrix. So we got a 2D picture, right? Okay. But the point is our data is collected from the 3D object. And the body is in 3D. Our human is 3D. We live in the 3D world, 3-dimensional world. So that's the first thing. So right now we got an idea. The image is a 2D object. So if we want our image to show something, we got it need my friend need, how can I say it, different colors. All right, different colors in each point on the image. So we got a pixel. Pixel is a minimum, it's the smallest element of our picture on the image. So we divide it into pixels, right? Pixels, right? So because we got data from all our body part. So from now, after the calculation from the computer, our computer, we got an exact, my friend, we got an exact number, house view number of each pixel. So what house view number used for? So let me remind you a little bit. House view number, we will use it, and we will label it to the image grayscale. I just want to give you a quick summarization, because eventually we will go into the detail how we control the grayscale of the image later on. This will be described in the lecture 4, chapter 4, image display. Right now, we just need to know, after the raw data is processed, our pixels in the image will be assigned a particular, every pixel, my friend, is assigned a particular house view unit. So that's it, because from the house view unit is to the grayscale, to the gray value, is just way more simple. So means right now we got an ultimate data right now. The grayscale is just how can I say it? The image grayscale modification is just It's not a data manipulation right now. It's just a modification process. So that's the reason why you gotta know. You gotta know exactly in here. I want a note right here. After our raw data is processed, one hash field unit value is assigned to each pixel, not one hash field unit. Okay, remember, not a gray value. Okay, a gray value. Okay, it's a hash field unit, totally different from the gray value. Gray value is a modification process, not the data manipulation process. Okay, let's go. So right now let's talk about the comparison. So one of the most important part we talk about when we talk about image data and the raw data. Yeah, this is the storage P they need to be storage. So the image data just require about 1/5 storage space compared to the raw data. That's it. That's all little fact for you, my friend, for you. And okay, let's see. And I got another two little notes for you right here. Data minute. Okay, understand it. So first of all, delete. Here is, my friend. Here is the image data. So one of the another thing when we take into account the comparison between the image data and the raw data is the image data is limited in the data manipulating process activities. Why? Because as I said you before, our data right now is finally calculated. So the calculation process is totally complete. So right now, the only thing we can change is a window wise, window width, window value, window width, window level. Just not a data manipulation. It's just, my friend, it's just a data modification. Just we change the grayscales. I will describe the detail on the chapter 4 image display. Okay, so compared to the raw data, our image data is limited in the manipulating process. Okay, limited means we can do many things with the raw data than the image data. Simple. That's the reason why the raw data will require more storage capacity than the image data, my friend. So the second thing we can manipulation process is limited. So what's about the measurements and the analysis activity? Yeah, analytical activity. So we can have, my friend, how can I say, we can have analysis on the image data. Yeah, we can have it by one of the most common numbers, which is displayed on our screen. Yeah, in a modern city system, they will be displayed on the screen automatically. When you use the mouse, you use the mouse to rolling it into that point. They will show you those numbers. First of all, the house field unit. House field unit of this point. Yeah, we will draw the mouse. Yeah, this point. Hey, and second of all, you got a standard deviation. What is standard deviation? Standard deviation is from a statistical definition. Standard deviation tells you how much variation of your data. How much variation of your data. For example, if your average is 1, but the point is it's your average from the 1 to 3. The average is 2, right? Yeah, the average is 2. But we got another example, like a number like how can I say it? -5. Okay, let me text you. Okay, it's just a little math. Doing a little math, and when we do a math, we should write it down. Yeah, my friend was once in a college. No, I'm sorry, in high school. I was in a special class for the special talented person of mathematics. So, but my trick is simple. Whenever you're facing the mathematical problems or issue, just write it down. Just write it down. You will get your answer easily. Okay. So, called 1, 2, 3. 1, 2, 3. Okay. It's a number. It's average is 2. Okay. Let me check. Okay, yeah, 2. So we got a number, not number. Okay, it's a plus 5. Really? Do I need one do this? Plus 5, yeah. The 4 and 5, right? 4 and 5, right? Got an average 2. Maybe we got another. What about plus 100? And we got a negative 100 and plus 100. Okay, for average 2, still 2. So what is how can we describe this array? Hey, the average is not enough, and the house field unit is the same. House field unit this time for this point is just an average, and we're gonna need another trait characteristic to how can I say, to picture our arrays of number comprehensively. So that's the reason why we got a standard deviation. So just a little explanation for you, my friend. We will go into this way more detail in another day. Okay. So we got the house field unit, or you can say more exactly the average house field unit of this point, and then you get a standard deviation of the whole image, my friend. Yeah, and you will see, you will know what is, because every single, yeah, you can see right, every single part of your body, every single part of your body is usually assigned with a particular range of house field unit. So you will know, my friend, based on the paradigm, the paradigm or the chart of the standard deviation of the house field unit of your image, you will know what is the kind of material cover the most of your picture, your body part right now, right here, or in the region. Yeah, for example, you got a calcification at some area. You need to know, right? It's a kind, because calci will get a higher house field unit than the soft tissue. So by analyzing the this area standard deviation of the house field unit, you will know there is a classification that you're in your body part at this point. Okay, and what is another characteristic you can analyze it? So we got a distance. Analyzing this distance is okay. It's just in a modern city system, you can do it easily by you take this point, you take that point, and it will give you the exact number in real life, in real body part, right? Because it's got I'm gonna say it got a coordinator. Yeah, we got a coordinate in that our computer processor unit. So you got a real distance from in life. Yes, you got a how much how long of that tissue, how long of that damaged tissue, how long is a calcification area. So that's it. Distance has few units, then deviation. But my friend, as I say above, it's just a measurement. You can analyze it, but the point is still the ability to data manipulation is still limited. So that's the reason why we need raw data to do some cool stuff, my friend. And image data, yeah, that's cool. But sometimes there's a trade-off. You need a more elegant display. You gotta sacrifice your data I mean your data space, your amount of data. So that's it. That's the data types. Let's go to another section, okay? Let's go to another section. Let's talk about the overview of image reconstruction. Oh my gosh, yeah. This is a huge part, my friend. Huge part. Okay, let's go with it. So, how can I say it? Like, just start from the little things first, okay? First of all, let's talk about definitions. Easy definition first. We got three simple, basic definition in here. Array, the array zoom, and the view. Okay, what is an array? What is an array? The array is an X-ray path, just like that, just like that. And I will give you the illustration later on. Okay, I put in here so many illustrations for you to understand all the things I've talking. So be cool, my friend, be cool. First of all, the array. Second of all, the array sum. The array sum. What is ray sum? Ray sum is kind of measurement of X-ray attenuation. And the view, complete set of ray sums. Okay, so let me show you. Let me show you. Definition sometime, my friend. Do you feel the same? Because in mathematics, if you solely read about the definition only, you can't get it. And for example, what is a number? Yeah, and even though I was in a special class for a talented person in mathematics, I don't know, I still have an irritation whenever I read the definition, or you mean the academic definition of mathematical definition of terms. Jesus Christ. So let me show you, alright? Let me show you. First of all, ray. This is the ray. X-ray path, okay? X-ray path, this is the ray, alright? And the ray sum is a measurement of X-ray attenuation. Means the it's a you can understand it just like it's a result of the process going through of X-ray beam through your body. So after going through your body, right? Okay, we got a ray sum because detector got that because the detector measure your remaining X-ray. And in another word, you can say that you can call it the measurement of X-ray attenuation because the X-ray beam will be attenuated a little bit, a part of it, after going through your body. All right. And the third one, the last one, view. The view is a set of X-ray sum because, my friend, our X-ray beam contains so many X-ray, a little single X-ray beam. All right. And yeah, we can call it. So the view is our whole. This is one ray, two ray, three ray, X-ray, right. There are so many beams. There are so many beams. There's fan beam. If one fan beam includes so many, I want to say single pencil beam. You can imagine that, okay? You can imagine that. So we gotta. So this is all of it is a view. Views, or you can say it is a attenuation profile. What is it? Attenuation profile is a number. It's a number of a ray, all number of a ray sum, of a set of ray sums. Attenuation profile. So, for example, you got a view right here. View. Is it a view? All right. And you got a attenuation profile. You got a measurement of all X-ray. Oh no, all ray sum profile. And when you got an all profile from all angles. Angles mean view, my friend. Angles mean view. So one view, you change the view, you change the X-ray tube angle. So from all angles mean all views. So you got and each view you will have one profile. And when you have a profile, attenuation profile from all angle, my friend, just like that, you will have the equation, my friend. You gotta how can I say it? Attenuation profile of all, my friend, of all points of your body part. Here. So let me introduce you. So and you from that point you got a all view, and you will use a little bit algebra to calculate it for you the exact house field unit of that point. That's it, my friend. That's it. So I got a little note right here. Attenuation profile for each field. And you got an attenuation profile for all views, and you will turn it to matrix data. So you see right here, right? It's a ray, right? A ray sim, yeah. You got an attenuation profile, one view here, one here, one here, one here. Again, you got all data, yeah, you got a formula equation, yeah, you got equation, you got a formula. You use a little bit algebra to help you reconstruct. My friend, that's math, a little math. Don't need to worry about that, okay? Don't need to worry about that. You just understand that you will receive, oh no, my friend, you will receive all the attenuation profile, all data from all views of your body part, and from that point, the mathematicians or our computer will help you to trace back from that data, trace back to your exact number, house field unit number of your body part at this point. Just like that, my friend. And that process, we call it back projection. Yeah, let me introduce you a little bit again, okay? You got data from all view of your body, and from that point, you will call math to help you trace back the house field unit of that point. So that we call it back projection process. What is back? Back is called back. We got a data, but we don't know what is it, and we will use a little bit. How can I say? We will use a little bit mathematics to trace back, to guess, my friend, to guess what exactly this point. What exactly is that is points? Okay, and projection means your data, your attenuation profile, each has a little projection, just like the thing you view a dog from many angles. Projection, my friend, and that's the reason why we call it back projection process. That's it. That's simple, my friend. And back projection is one of the most popular technique of CT image reconstruction till now. Yes, also sometimes we call it a filter back projection, FBP, and sometimes you got a adaptive statistical back projection, yeah, ACR, doesn't matter, my friend. The base you gotta just need to understand the most basic thing of back projection. Just like that, the thing hey I've said before. This is back projection process, and welcome, my friend, to one of the most important terminology in CT application, my friend. Woo! Back projection. All right, let's go to the next slide, okay? Well, oh my, filter function. So this is the reason why people call it the filter back projection algorithm. Oh shit, I'm sorry. FBP. FBP. So usually you would call it even until now. People will talk about back projection as just one of the most important technique in image reconstruction. So we know we got a terms of back projection. What is back projection, right? So let's talk about the filter. Why we need a filter? So just imagine, all the time you will you take an app from an iPhone, from an Android, you want to be more beautiful in your images, you will put on the social media, right? And you will use the app, and in that app, it will have a kind of like a filter. And after you use your image, going through the filter, your image will, yeah, there are so many consequences according with many filters. So it may help you to be more white. I mean, the light will be lighter. It will be darker, or the attenuate the you will got some effects on your face. Okay. So the point is, my friend, the filter is used for you want to change the way your image is displayed. So let me show you. So what is the filter under the mathematical view? Let me show you. Back to the front. So the filter. Oh, what? Hmm. What is it? Okay. So the filter is simple. The filter in a mathematical perspective is just a matrix, because your image is a matrix, right? A matrix with a number attached side to each pixels. So right now you can need a filter because you do some algebra, just a filter. You will do some algebra to change the way your image will be displayed. So that's it. It's just a matrix of number, and there are so many filter, which is called, and one of the most famous filter name is convolution filter, or you could call it kernel filter matrix. And if you got a time to, how can I say, to visit some deep learning or machine learning websites or blog or forums, you will see this term, yeah, appears many times: convolution process, convolution filter, and kernel filter matrix. Okay, then we just need to remember the main point of filter. Filter help you to change the way that you want your image will be displayed, just like that. By you take some algebra activities in there. Okay, okay, and there's a little note right here. You apply the filter only for the raw data, only for raw data. So, sorry. And how can I say it? Because, my friend, as I said before, our image data is limited in a depth manipulation activities. So you can apply the filter only for your raw data. You can't apply it for the image data. And sometimes, as I said before, to change, you can change the window width and window level, but that's not a data manipulation. You just change the way the image is viewed, and we will talk detail about it in the next chapter, next lecture. Okay, okay. So the point is, my friend, the main question is does filter really help you to how can I say it? Help you to increase the image quality. What? Because if that was true, why don't just people use a filter all the time, increase it, use it, use it, use it, use it, use it, use it, all the time? Why don't people just use it? So the point, my friend, our data is limited, and the improvement will be limited too. So there are my friend, two main. Uh, there's some popular goal when you want to use filter. First of all, you want to smooth your image. So, but there are always the same, my friend. The rule is there are always the trade-off of using it. First of all, if you want to smooth your image, you will reduce the difference between the adjacent pixels. But the point is, you will sacrifice the spatial resolution. So this is the main point. Sometimes the doctor asked me why the images from this manufacturer is so, I don't know, there's a, how to say it, there's so many dots in here. Yeah, and they feel like there's no smooth no smooth, my friend, and they tell me they don't like it, but I tell them the smooth is just like maybe just like a function. And how can I say it? And yeah, it's just like an app, and every single vendors has their own app and their own strategy. So maybe there are always in time there are the more smooth your image. In the case that two models of you is equal about in the technological configurations, maybe they are just applying the filter. So the filter maybe it will help you comfortable about the image. The point is really choose. You eventually sacrifice the spatial resolution of your image. So is it good or bad? I don't know. But I think, personally, I think you should view it in a both way. Okay, in a both way with filter or without filter. Okay. So that's the goal for the first goal. Or sometimes you will use the filter to optimize the spatial resolution, but the point is, just like a reverse effect, you will sacrifice your low contrast resolution. You will see the batteries between the organs, between the tissue, between the part, the parts right now is clearly. But the point is, you can see the battery, but you can how can I say that? You can see the differences between the gray scale, gray value. You can recognize it because you've sacrificed the low contrast resolution. So that's the point. That's the point. So what is advice? Two side. Um, there are two ways. First of all, okay, we write down. Okay, and we write down the two recommendations. First of all, you can see both ways with filter, without filter. Okay, see both ways. Will help you because in each way you can adapt with it and you won't feel uncomfortable or inconvenient when you face the model that won't use that filter in the default setting of its machine. Okay, that machine. So it's both way. So the second view is choose one uh setting. So I think it's a great. Okay, just like in financial state analysis, you will borrow a thing, so borrow money to take to get a project starting. But the point is, even though you got a cash in your pocket, the point is you got a tax rate, you got a tax shield, right? You got a tax shield, and you gotta be balanced. The tax shield will protect you from paying more after tax, but probably the more you borrow, the more risky you are. Okay, the more risky you are. So choose one setting to compensate both things: the low contrast resolution or the high contrast resolution, which means the spatial resolution. So two ways. Depends on you right now, my friend. Depends on you right now. So that's it. That's a slide 4.1. That's a no. I'm sorry. That's a section 4.1 field functions, and section 4 of our part 2 overview of image reconstruction. So I think we should end today because I'm right now need to eat something. Uh, I've been using so many energy, so much energy today. So I will meet you in another day. Okay. Hope your day goes well and yeah. Oh, happy Christmas. Wish you got a. I wish you got a happy time with your family. Always, my friend. Always think about your family. Yeah, be there for them. For them. And I'll be back, my friend. Maybe after the Christmas. I don't know. There are many works need to be done. but I will be back at my convenience. My friend, peace. Goodbye.